Good morning, AP Physics students. It is Monday, March 30th. We are still learning momentum, and you should have gotten an email about the fact that you only have school Monday, Tuesday, Wednesday this week. They've canceled Thursday and Friday for students. Teachers, we're going to be doing some more training and planning because you should have also gotten then that email information that there's a new school day of an intentional online school day where you will be in class from like 9 to 12:30 with your teachers learning. And the idea is that we're going to do that like Monday, Tuesday, Wednesday, Thursday, and then Friday you'll be able to work on things. Just trying to structure things so that way we have some kind of a regular school day designed to be an online school, which we don't really have right now. So that's kind of the plan. None of that will start until after spring break. There'll be some more emails about it. But if you did not get any email at all and you have no idea what's going on, try to reach out to the school because there's definitely been some emails going out. All right, so let's go into these bell works. So these are both review. One of these is an elastic collision. The other one is an inelastic collision. The inelastic is a lot easier to solve. The elastic one, you got to use a couple of equations. See if you can remember how to do them and then hit pause. And then I'll go over how to do them in a second. Okay, so these are good AP style questions that have no numbers at all. This is kind of a lot of ink on the next slide, but I'll work through it. The first question, all of these conserve momentum. So that's the thing is that momentum is always conserved. And instead of writing momentum final like that, I'm going to be writing it like this. And it just helps out when I have a lot of subscripts to keep track of things. Like this is velocity of A final plus velocity of B final. So those little ticks are called prime. So this is a momentum initially equals momentum on final, or if you want to speak like a math person, P equals P prime. But as a physics person, we'll say momentum initial equals momentum final. All right, so the momentum initial is 2m multiplied by v, 2mv. The other object isn't moving. And then they're going to stick together, inelastic, stick together. And when they stick together, we got to add their masses together. That's velocity final right there. 2m plus m is 3m. We can divide both sides of the equation by m, canceling m out. And we have 2/3 v equaling v final. There's our answer right there. Not too bad. Inelastic collisions do not conserve energy. But elastic ones do. So for this one, you have you actually have to use two equations though. You notice if you write out your conservation momentum here, we can kind of expand that out with the objects. Its velocity is just v, and then afterwards when they collide, we have m times velocity of A final plus m times velocity of B final. You can divide everything by m, but you're kind of stuck right here. I don't know what either final velocity is. I need another equation. Well, this thing conserves kinetic energy, but in yesterday's lesson, we learned that while that is 1 half mv squared plus 1 half mv squared, the squareds are really annoying. And then it's easier to use this form right here. So that one literally says velocity of A plus velocity A final equals velocity of B plus velocity B final. And if that equation looks like magic, you need to go check out Friday's lesson where I show you where that comes from. It is a very useful and very necessary equation. All right, so using that equation, velocity B initial was 0. So that's actually what the equation looks like when we plug in our values. And here's the thing. Velocity A at the start of the problem, that's called V. So we're gonna go ahead and we're gonna go ahead and plug that in. We'll call that V. And then we'll notice that velocity B final, I'm gonna grab a different color here. Velocity B final, well, that's right over here. So we can actually substitute in. So we're gonna go ahead and plug in right here and keep grabbing colors. This is getting plugged in right there. And so now we're down to just VA primes. Solving this, if we subtract v from both sides, it disappears. So we get that it's 0. That actually is what happens. This object will stop and it'll make the other object go. If you've ever played pool before, this happens all the time. When two objects have equal mass and they collide and it's elastic, one stops, the other one moves. So that answer is actually correct. All right, so kind of a long bell work, but it's actually a really short lesson. So let's dig into it. Today's lesson is called the ballistic pendulum, or as I call it, the block and the bullet. And basically, it's you've got a bullet and it's hitting a block. It's going to stick inside, and then the block is going to swing up into the air. And what's interesting about this problem is that I had no idea how to do it in high school. I got it wrong a lot. And that was because in high school, I really loved the formula work plus energy initial equals energy final. I thought that thing was great. It got me all kinds of answers. It was easier than Unit 1 and Unit 2 and Unit 3, force and motion. I just felt like cheating. No angles. It was wonderful. But I tried to use it here, and I got the answer wrong. And it was weird because like I get the answer close, but it'd still be wrong. And the problem is right here. See, what I was doing is I was going, all right, 1/2 mv squared, and putting in the velocity of the bullet. And then I was going, all right, m plus m. I'm not going to forget about the masses added together. mgh, potential energy due to gravity. And I was trying to make them equal to each other. And the reason I couldn't do that is because work happens right here. Now, if they tell you that it's 10 joules of work or they give you a value, then sure, we can use this. However, that's not usually pretty common. Usually we don't know how much work happens there. In fact, that's what you're supposed to figure out on our next problem. And so you have to use conservation momentum because this is inelastic. The objects stick together. And so that was the problem, is that I wasn't paying attention to the momentum unit and I was trying to use energy because I saw something swinging up to a height. Got to use momentum. And sometimes you have to use momentum and energy to solve problems. But let's take a look. All right, so we have a block of 5 kilograms. It's hanging, and it's right here. And then it's hit by a 0.5 kilogram bullet. It causes it to swing up to a height of 2 meters. And so the question is, how fast was the bullet originally moving? So here's the idea behind the question. Momentum is always conserved. And so what that means is you have this bullet, which has a mass of 0.5, going to hit this block, which has a mass of 5. During this collision, momentum will be conserved. And that will allow us to then figure out what is the velocity final. Then, that velocity final can be featured in a formula that involves conservation of energy, as in 1/2 m. Be careful though, because in this case, m is 5 plus 0.5, because it's both masses. I'm just going to write that as 5.5. Sorry if you can hear screaming baby. V prime squared equals 1/2 5.5, I'm sorry, mgh, which is just 5.5, g is 10, and then h. So the idea is that you need to use a conservation momentum to figure out, let me grab a highlight here. You gotta use a conservation momentum to figure out how fast it's moving after collision, and then a conservation of energy to figure out how high it swings. And you gotta be very careful because um, your initial velocity kind of becomes a final velocity. What I mean is that here you have an initial velocity that I don't even know what it is. That's actually what you're asked to figure out. And then later on, you have this velocity final, which is then sort of treated as an initial velocity for swinging up. Well, I got all the math on the next page. We'll walk through it. And then you'll give it a try on homework and see how it goes. All right, so I'll walk through this. The first thing that I wrote out was they asked how fast was the bullet moving? And I actually didn't include in the problem how much energy was lost, but I went ahead and calculated that also. So the first thing I wrote out is actually based on the energy. So up here, that formula is to figure out how much energy is lost, which isn't actually needed until the very end of the problem. Um, and so let's start off with actually solving the problem first of just how fast is the bullet moving. Okay, so we start off with our conservation of momentum right here. Momentum initial equals momentum final. And we write it out and we have a problem. The problem is we can't solve that because we don't know the initial velocity or the final velocity. So we're stuck. So we're going to need to write another formula out. And so the formula we write out is this one right here, which is a conservation of energy. Because since we know the object goes to a height of 2 meters, we can then solve for how fast it must have been traveling after the collision happened. And so we find that the velocity it had after collision is 6.32. It's square root of 40. So then that becomes our final velocity we weren't able to solve earlier right here because we didn't know how fast it was moving post collision. But now we do. So we can plug that in, which you'll notice I've done right there. And then we can get the initial velocity of the bullet, 69.5 seconds. That bullet was going really fast and slowed down a lot. We went from 69.57 to just 6.3 because the block was so massive, and after the collision it slowed down. Once we solved for that, we've answered the question they asked. How fast was the bullet moving? I forgot what question I even asked when I wrote this out. And so we're done. But the homework actually asks you for how much energy was lost. And so I actually went ahead and did that also. So you can see I wrote out the initial kinetic energy plus work equals final potential energy. And then I actually did the calculation down here. I lost a surprisingly large amount of energy. I checked my math a couple of times. But yeah, just a lot of energy is lost in the bullet enters. We can see we go from over 1,000 joules to just barely over 100 joules of height energy. And I did keep track of my masses properly. We just have the mass of the bullet here. Here we have the mass of both objects together. So a lot of work went into putting that bullet into that block. All right, give it a try on the homework, and I'll be online. There's a different office hours this week. Office hours is going to be from, should have been in the email, but it's like 10 to noon Tuesdays. And so check there if you want to talk to me about this lesson. Other than that, I'll probably see you in class after spring break. Stay safe, everyone.